Hi guys, Sajjad Hussain again with another video. This video is in continuation with my previous video where I stopped the video till the definition of my loads, and I just run for one time just to check the correctness of my model, and we saw that the model was okay. Now I'm going to modify the model to suit the conditions which are specified in the example, number one. Number two, let me modify the seismic load for especially for the time period. Now in my previous video we defined the seismic load in case in x direction and in y direction. As per the plan, our x direction means east-west direction and y direction means our north-south direction. So in x direction, as mentioned, that there is no shear wall, the only moment resisting frame is the actual special frame. So to define the time period, here we have to select these two parameters, that is CT and X, carefully. How these are defined? These are defined in ASC 705 at table 12 dot 8-2. These are the values of approximate period parameters CT and X. Here you can see that their conditions are steel moment resisting frame or concrete moment resisting frame. So concrete moment resisting frame in X direction, the correct value for CD should be 0.016 and X should be 0.9. So for X direction, our proper combination should be 0.016 and 9. So that was the only change which I wanted to modify. So let us change this. So it's okay. And in Y direction, load pattern, in Y direction, the CT value is 0.02 and X is 0.075. So as per the last condition, all other structural system, it should be 0.02 and 0.75. So that is correct. That means now we can say that our seismic definition is correct. Now, if you remember, we defined the superimposed dead load and live load for all the floors as same. But we know that for the roof, the superimposed dead load and the live load was different. Live load for the roof was 20 pound per square feet and the live load, the superimposed dead load for the roof was only 10 pound per square feet. So let us modify the input data file. Here we can see the shell load, dead loads. Yeah. Let me close this one so it will be more visible. Now you can see 30 is shown over here. Our units are pound per square feet. So it shows 30 pound per square feet. and the level is, we should go to see the roof level, which is the 12th story at 148 feet. And now you can see that the dead load, gravity load, dead load is 30 pound per square feet. Actually, the superimposed dead load was only 10. So what we are going to assign here, or we are going to revise here, assign shell load, uniform load, and instead of 30 it should be 10 only, and we will select this replace existing load, apply. Okay, so we have to select first, select we can select like this, assign shell load, uniform, 10, replace, apply. So now you can see that at 12th story, where the level is 148 feet, that means at the roof the dead load is changed from 30 to 10. What about others? Others remain same 30. That means story 11, story 10, story 9, all remaining stories, they have the 30 pound per square feet. So let us save this condition. Let's go back to the rooftop. That means at 12th story, the superimposed dead load is 10. Similarly, we will revise the live load. Display, load assignment, shell, not dead, live, apply. Now you can see that the display shows 75 pound per square feet. We will change this. We will select the slab, assign shell load, uniform. Now live load, it should be replaced to 20 pound per square feet. Okay, so now at the rooftop, which is the 12th story, where elevation is 148 feet, our level is 20 pound per square feet. What about other levels, other floors? 75 pound, 75 pound. So all other floors have 75 pound per square feet. Let us save this model. That means we have revised the live and dead load according to the conditions given in the example. Now one more thing we have to define. We have to define the internal columns. The internal columns were 30 inch by 30 inch, so we have to assign 30 inch by 30 inch for the internal columns. So what we have to do, we have to define section property, frame section. Let us select this concrete column exterior, and we can say add copy. So we will say this will be concrete column interior, and now interior columns are 30 by 30. All other parameters will remain the same. Okay. Now we will go to elevations. 1, apply. Now we can see these are the exterior columns, and here we can see that this is number 1, that means this is again exterior. So that means let's show the plan first. So what we have to select, we have to select all columns on grid 3 and all columns on grid 2, but they should be within B to G. That means all these columns should be revised. So let us go to elevation. Elevation 2, apply, and now we know, let us deselect all. Now we have to revise these columns. Let us select these columns. These are the internal columns. Assign, frame, section properties, internal columns. Okay. So now you can see that these are the internal columns and these are the external columns. Similarly, we will select elevation 3, and here is still these are external columns, but we will revise to interior columns. 1, 2, 3, 4, 5, 6. So now assign, frame, section properties, all interior columns. Fine. So let us save the model. So now up to this point we have defined our model correctly. So let us select a 3D view and undeformed shape. I don't want to show anything. So this is our model, which is in line with the model defined in example 29.1. Now we have to define walls. So far we have not defined walls, and if we see the plan, the walls were on grid B between 2 and 3 here, and on grid G between 2 and 3. So we will define wall over there. Let's select elevation at B, and then later on we will go to G. So this is elevation B. Now we have to define wall. There is only one wall. We can define all these walls like this. Quick assignment. Let us save. Similarly, we can go to elevation G and assign wall sections. Save. So now our definition is complete with the walls also. Let us run one more time. And we will see, is there any difference in the deflected shape because of the walls? There should be. Now you can see the deflected shape is a bit different. Here at the walls the deflection is less, whereas at other locations the deflection is more. If we animate, we will see this is because of the dead load. Exactly. So this is the true behavior of the structure. We can stop this animation. So far we have defined our geometry as per the model given in the example. Now we have to define these walls as pier. Okay. Select properties, wall sections. Okay, and then we can assign this shell as pier P1. Okay, that will be helpful in designing the walls when we will go to design level. So we should save the model. Now we have to define load combination. We can add new combination manually, or we can select add default design combination. These are the selections are steel frame, composite beam, concrete frame design, concrete shear wall design, concrete slab design. So we will select concrete frame design, concrete shear wall design, and concrete slab design. Right? So all these combinations are generated as per ACI 31808. If we want to see any combination, for example this, so we can select that combination and we will say show or modify. So dead load is 1.2 times, wind is 0.8. So all these possible combinations are selected over here. So a lot of combinations are there. So we have defined combinations also, and now let us analyze for the last time. This is the final analysis, because we have defined the loads individually, the dead load, the live load, the seismic load, the wind load. Then we defined the load combinations. All the geometry is defined as per the model. So our input data is complete so far, and now we are running the model for as a final version. So the run is complete. We can see the deflected shape. We are not interested in deflected shape, so it's okay. We have already checked that the deflected shape in all the load cases are okay, in fair agreement with the model. And now we are going to design what? Design the concrete frame. Let us view the preferences. Our design code is ACI 318. Multiple response design case, step by step, all iteration, etc. Now seismic category is D. Row should be 1, that's okay. SDS is 0.5. Now design system these are SDS are taken from chapter 12 of ASC 705. This is used to combine the load combinations here, especially for vertical loads, etc., where SDS is design spectral response acceleration parameter at short period, and we have to select as per section 11.4. So if we go back to section 11.4, we can see what is SDS, and we have already defined the SDS. So here SDS comes out to be correct. All other parameters, phi, etc., they are okay. That means these parameters are okay. Now concrete frame rebar selection, let us leave this for default values. For the beam also for default values, select design combinations. All okay. Now we have started the design. You can see the members are being designed one by one. So first beams were designed, now columns are being designed. So still ratio as shown, we can select we can check the design also, but now let's go to concrete frame design. We have a check. Verified design versus analysis versus design sections. These are okay. Now we can go for shear wall design. Same thing, all these parameters, these are taken from there. Okay. So let us start design. Now the column, the walls are being designed. Then we can go to concrete slab design. Okay, these are the default values. If you want to change, you can change. Let us start the design. Select all. Okay. Still the slab design is running. So now you can see the design of the slab. Reinforcement details are shown. We can check, but this looks logical. Now we will go to detailing. Detailing preferences. Units are US standard units. Length is feet, sections are in inches, rebar is spacing in inches, forces are in kip. So let us leave for the default. Start detailing. Now you can see that a lot of drawings are generated. Here, for example, the list of drawings, various sections, beam section, column section. These are the standard one. For the slabs, the slab details are there. So all this information is there. So once this detailed information is there, that means now you have completed your detailing arrangement also. These are the drawings. You can open these drawings in AutoCAD. So far all these details are available. You can go and check one by one all these details. A very detailed set of drawings are available. Similarly, we can generate report. If you go for detailed report, it will be a very hectic, long sort of report. We can generate summary report quickly, but it will take time. So here you can see this summary report is generated, but of course it takes time. This is the summary report. and you can go through it and you can check and modify accordingly. So far we have seen our model, 3D view, drawings, report, etc. So now this concludes a complete session of defining the input for a model which we can analyze in Etabs. And from the very beginning, as I explained to you, we define the sections, we define the geometry, we define the loads, the vertical loads and the lateral loads, load combinations, everything. And then these are the final set of results. Now I have already verified and these results are in well agreement with the manual calculation. So we can say that we have a good design of a structure in Etabs. So thank you very much for watching and your appreciation. If you have any comment, please do not hesitate to send me an email. Hopefully I shall be able to answer you quickly. And please, because of my involvement with other assignments, if it's a little bit delayed, but make sure that your queries will be answered. So thank you very much. Bye.